Space isn't just silence and darkness, it's alive with whispers we can't quite decipher. Imagine a sound so bizarre, so alien, that it reaches across billions of miles to echo through our radio telescopes, defying every explanation science can muster. These aren't sci-fi sound effects, they're real, unexplained signals from the deepest corners of the cosmos, each one a cosmic riddle waiting to be solved. Some pulse with eerie regularity, like a heartbeat from the void. Others scream into existence for mere milliseconds, vanishing before we can trace their origin. And then there are the ones that repeat, looping back like a message no one's meant to understand. For decades, astronomers have strained to listen past the static, hoping to catch a signal that might change everything we know. But what happens when the universe sends back something that shouldn't exist? A burst of energy too powerful to come from a star, a pattern too precise to be random noise. A frequency that makes no sense in the laws of physics as we know them. These are the moments that blur the line between discovery and mystery, where even the brightest minds can only shrug and ask, what is that? Today, we're diving into 25 of the strangest signals ever detected, each one a story written in the language of the cosmos. Some might be collapsing stars or distant black holes. Others, well, that's where things get interesting, because whether it's the infamous WOW signal that vanished without a trace or the chilling Lorimer burst that rewrote the rules of astrophysics, these anomalies remind us how much we don't know. So grab your headphones, we're tuning into the universe's weirdest frequencies, and trust me, you'll never look at the night sky the same way again. The night of August 15, 1977, started like any other at Ohio State University's Big Ear radio telescope. Glued to the printouts streaming from the machine, astronomer Jerry Amon scanned the data for anything unusual, but nothing could have prepared him for what came next. A surge of radio waves, 72 seconds long, blasted through the constellation Sagittarius at exactly 1422 megahertz. It was so intense, so perfectly concentrated, that Amon circled the alphanumeric code on the printout and scribbled a single word beside it in red ink: wow. That signal wasn't just strong, it was unnatural. It matched the exact frequency hydrogen emits in space, a logical choice for any civilization trying to announce itself across the stars. But here's the catch, it never repeated. Despite decades of listening, turning every telescope toward that patch of sky, the silence has been deafening. So what was it? The leading theory points to a comet, except no known comets were in that region when the signal hit. Others argue it could have been a passing satellite, but military records show nothing was transmitting at that frequency. And then there's the unsettling possibility. What if it was intentional, a cosmic hello flicked our way by something or someone, just once to see if we'd notice? The WOW signal's legacy isn't just in its mystery. It's a reminder of how fragile our connection to the universe really is. A whisper slips through the noise and we're left staring at the static, wondering if we just missed the call of a lifetime. For decades, the WOW signal stood as a cosmic ghost, undeniable yet untraceable. Then in 2017, a team from the Center of Planetary Science proposed an answer that should have solved everything: comets. Specifically, two known comets, 266P and 335P, passing through Sagittarius around the same time in 1977. Hydrogen clouds surrounding these icy bodies, they argued, could have reflected radio waves right toward Earth, creating that infamous spike. Case closed, except it wasn't. Astronomers quickly punched holes in the theory. The Big Ear telescope's design made it nearly impossible for a reflected signal to appear that focused. Worse, those comets weren't even in the right part of the sky when the WOW signal hit. The team's own data showed a glaring mismatch in coordinates, leaving the comet hypothesis dead on arrival. But the real twist, even if comets had been the culprit, their radio signatures wouldn't match the signal's clean, narrowband frequency. the very detail that made it so intriguing in the first place. So why does skepticism linger? Part of it's the signal's eerie precision. Natural cosmic noise tends to be messy, smeared across frequencies. The wow signal was laser sharp, like tuning into one perfect note on a radio dial. Then there's the silence. If it were a fluke, a quasar, a glitch, a passing asteroid, why haven't we caught anything like it since? Modern telescopes scan thousands of times more sky than Big Ear ever could, yet that 72-second burst remains stubbornly unique. Some researchers whisper about interstellar scintillation, a phenomenon where distant signals amplify briefly as they pass through cosmic dust. Others wonder if Earth's own atmosphere could have bent a mundane signal into something extraordinary. But with each new theory, the same question echoes. If it was just space, weather, or equipment error, why haven't we replicated it under controlled conditions? The longer the wow signal resists explanation, the more it taunts us not just as a mystery, but as a lesson. However advanced our tools become, the universe keeps a few cards close to its chest. Fast radio bursts usually play hard to get, flashing into existence just once, vanishing before we can even pinpoint their origin. But FRB 121102 broke all the rules. Discovered in 2012 by the Arecibo telescope, this signal didn't just scream into the void and disappear, it came back again and again. At first, astronomers thought it might be a glitch. Then, in 2016, the same burst erupted over and over, pulsing with eerie consistency from a tiny dwarf galaxy 3 billion light-years away. What makes this repeating signal so unsettling isn't just its persistence, it's the raw power behind each blast. In mere milliseconds, FRB 121102 unleashes more energy than our Sun emits in 80 years. And unlike one-off bursts which might be explained by catastrophic cosmic collisions, this one's regularity points to something far more deliberate. Theories range from the plausible to the downright wild. Some researchers argue it's the death throes of a magnetar, an ultra-dense neutron star with a magnetic field so intense it twists space itself. Others suggest it could be a pulsar on steroids, spinning so fast it periodically rips open magnetic fault lines, shooting out hypercharged radio waves like a cosmic lighthouse gone haywire. Then there's the fringe idea, the one that makes scientists shift uncomfortably in their seats. Could it be artificial? The signal's precision and repetition have fueled speculation about alien megastructures, like a colossal beacon or even a power source for an advanced civilization. But here's the catch: even if we entertain that thought, the numbers don't add up. A transmitter that powerful would require energy harnessed from an entire star, and if someone was broadcasting, why aim sporadic bursts in our direction? The real breakthrough came when astronomers traced FRB 121102's home, a dim, unassuming dwarf galaxy brimming with young stars and turbulent magnetic fields. That environment lines up neatly with the magnetar theory, but there's a twist. Another repeating burst, FRB 180901J, was later found in a completely different type of galaxy, one quiet and aging. Suddenly, the mystery deepened. If repeating bursts can emerge from SUCH Chinese letter Chinese letter Chinese letter Chinese letter Chinese letter environments, could there be multiple cosmic engines capable of producing them? For now, FRB 121102 remains a tantalizing puzzle. It's a reminder that the universe loves to defy our expectations, serving up phenomena that blur the line between natural wonder and something almost intentional. Every time it repeats, it's as if the cosmos is teasing us. You're getting warmer, but you're not there yet. FRB 121102 didn't just repeat, it rhythmed. When astronomers passed its bursts, they uncovered something extraordinary, a pattern hiding in the chaos. Every 157 days, like clockwork, the signal would erupt in a flurry of activity, firing off multiple bursts over 82 days before falling silent for another 75. This wasn't random noise, it was a cosmic metronome ticking with precision across the void. The implications were staggering. If the source had a schedule, it meant the environment around it wasn't just turbulent, it was orchestrated. This cyclical behavior pointed straight to a magnetar, but not just any magnetar, one locked in a deadly dance with another massive object, perhaps a black hole or a companion star. As the two orbited each other, their gravitational tug-of-war could warp the magnetar's crust, triggering periodic quakes that unleashed those iconic bursts. But here's the catch: no known magnetar orbits anything dense enough to produce such a clean, repeating timetable. Unless, of course, we're dealing with a breed of neutron star we've never seen before, one born in conditions so extreme it defies our models. Then there's the bursts themselves. While most FRBs are chaotic, FRB 121102's emissions had an eerie consistency. Their dispersion measures the delay in lower frequencies arriving slightly later, suggested they were plowing through dense magnetized plasma. That fingerprint matched the environment around a young magnetar, still swaddled in the debris of its explosive birth. But why would a magnetar, of all things, produce bursts this powerful? Even the most energetic neutron stars shouldn't crackle with such ferocity unless some unknown force was supercharging them. The real game changer, though, was how this signal rewrote the FRB rulebook. Before 121102, astronomers assumed all fast radio bursts were one-off catastrophes, collapsing stars, merging black holes, the universe's way of slamming a door. But here was proof that some FRBs weren't just cosmic accidents, they were systems capable of firing again and again. Suddenly, the hunt wasn't just about catching fleeting signals, it was about finding more repeaters, mapping their quirks, and piecing together what made them tick. And the universe delivered. When FRB 1809-01J started repeating from a calm, aging galaxy, it shattered the notion that FRBs only came from youthful, turbulent nurseries. Now the question isn't just what creates these bursts, it's how many different cosmic engines are out there, each humming their own strange tune. Every time a new repeater flares up, it's as if the cosmos is reminding us the rules you thought you knew. They were just the first page. Of all the signals that have ever teased the possibility of extraterrestrial intelligence, few are as quietly unsettling as SETI 02+14a. Picked up in 2003 by SETI ambitious Project Phoenix, this whisper from the Pisces constellation wasn't just another blip in the cosmic static, it was a signal that drifted. And that tiny detail made all the difference. Most natural radio sources stay locked to a single frequency, like a piano key held down. But SETI 02+14 slid slightly up and down the dial, shifting about 8 to 37 Hz per second. At first glance, that might seem insignificant until you realize this is exactly what you'd expect if the signal came from a planet orbiting a distant star. The Doppler effect, the same phenomenon that makes a siren's pitch change as it passes you, would stretch and compress the signal as the planet moved toward and away from Earth. SETI scientists had long theorized that an alien transmission would exhibit this very trait, and here it was, ticking every box except one. The signal was weak. So weak, in fact, that it hovered right at the edge of detectability, appearing in only 3 of the 9 observations aimed at its coordinates. That inconsistency left researchers torn. Was it a fleeting artifact of equipment glitches or something far more profound? A message just barely loud enough to brush against our instruments before fading back into the void. Even the most optimistic SETI analysts labeled it interesting but inconclusive, a frustrating limbo between breakthrough and background noise. What makes SETI 02+14 a linger in the scientific imagination isn't just its ambiguity. It's the setting. The signal originated near a patch of sky devoid of known stars or planets, a cosmic blind spot where nothing obvious could have produced it. No pulsars, no quasars, no flaring red dwarfs, just empty space and that drifting frequency. Skeptics argue it could have been interference from Earth's own satellites, but here's the hitch. The frequency matched the expected range for hydrogen line transmissions, the universal, watering hole frequency many scientists believe advanced civilizations might use to broadcast. Then there's the repetition. Unlike the WOW signal which vanished forever, SHB-02 plus 14 reappeared multiple times, but never long enough to confirm its origin. It's as if the universe was playing a game of peekaboo, flashing us just enough to keep us guessing. To this day, no telescope has pinned it down definitively, leaving it suspended between two possibilities, a cosmic mirage or the closest we've ever come to hearing a hello from the dark. Long before fast radio bursts became cosmic celebrities, there was the Lorimer burst, the signal that started it all. In 2007, astrophysicist Duncan Lorimer was sifting through old data from the Parkes radio telescope in Australia when he stumbled upon something inexplicable. A 5-millisecond blast of radio waves so powerful, it had traveled 3 billion light-years before slamming into Earth's detectors. The numbers were staggering. In that blink of an eye, it released more energy than the sun pumps out in 30 days, and then, just like that, it was gone. At first, even Lorimer doubted what he'd found. The signal was too intense, too brief, and came from a patch of sky with no obvious cosmic fireworks. Colleagues dismissed it as telescope glitches or even terrestrial interference, maybe a microwave oven left running near the observatory. But when follow-up scans found no faulty appliances or satellite reflections, the astronomy world had to confront a chilling possibility. What if the universe had just screamed at us and we had no idea why? The Lorimer burst didn't just defy expectations, it rewrote them. Before its discovery, no one imagined radio waves could pack such energy into such a fleeting moment. Traditional sources, supernova, pulsars, colliding galaxies, all left longer, messier fingerprints. This was something else entirely, a cosmic gunshot echoing across the void. Skepticism gave way to fascination as researchers realized they'd uncovered an entirely new class of astrophysical event. What made this signal so transformative wasn't just its violence, it was its loneliness. Unlike later repeating FRBs, the Lorimer burst never came back, leaving astronomers with only one tantalizing snapshot to dissect. That singularity forced scientists to rethink their tools. Telescopes designed to study steady, predictable objects suddenly needed upgrades to catch millisecond anomalies. Data analysis techniques had to evolve too, with algorithms now trained to hunt for needles in the cosmic haystack. The legacy of the Lorimer burst isn't just in the mysteries it posed, it's in the doors it kicked open. Within a decade, FRBs went from astronomical oddities to one of the hottest fields in space science, with dedicated observatories scanning the skies for these elusive flashes. And every new burst detected since, whether a repeater or a one-off, traces its pedigree back to that first, fleeting hello from the dark. It's a reminder that sometimes the universe's most profound revelations come not with a fanfare, but with a whisper and a challenge to listen closer. In December 2020, the Breakthrough Listen project picked up something extraordinary, a signal so precise, so unnervingly artificial sounding, it seemed to beam straight from Proxima Centauri, the closest star to our Sun. Dubbed BLC-1, this narrowband radio emission ticked every box for a potential alien transmission. It appeared at 982 MHz, a frequency typically silent in nature, free from the cosmic static that fills most radio bands. Even more compelling, it drifted slightly, the telltale fingerprint of a signal originating from a moving planet. For a fleeting moment, the possibility hung in the air. Had we just intercepted a hello from our cosmic backyard? The euphoria was short-lived. After months of painstaking analysis, researchers reached a sobering conclusion. BLC-1 was almost certainly human-made. The culprit, likely a malfunctioning electronic device somewhere on Earth. its signal bouncing off satellites or the ionosphere to mimic an extraterrestrial origin. But the real story here isn't just another false alarm, it's how close we came to being fooled. That drifting frequency, once considered the gold standard for alien detection, turned out to be replicable by terrestrial interference. The very traits designed to weed out human noise became its perfect disguise. What makes BLC-1 unforgettable isn't its disappointment, it's its lesson. For decades, SETI protocols assumed narrowband signals with Doppler shifts were safe bets. Now we know even those can be cosmic mirages. The irony, Proxima Centauri wasn't just any star. It hosts at least 2 planets, one of which orbits in the habitable zone. If there was a place to expect a signal, this was it, yet that proximity may have been the trap. Being so close meant Earth's own radio pollution could easily contaminate the data, a problem SETI rarely faces with distant stars. The aftermath reshaped the search. Breakthrough Listen now employs stricter filters, cross-checking potential signals against global radio interference databases in real time. But BLC-1's legacy lingers as a cautionary tale, one that proves the universe's greatest trick might not be hiding its secrets but convincing us we've found them. In 1967, Cambridge radio astronomer Jocelyn Bell Burnell noticed something peculiar in her data, a series of pulses so precise they seemed to tick like a cosmic metronome. Every 1.337 seconds without fail, a burst of radio waves would sweep past Earth, originating from a spot near the constellation Vulpecula. The signal, dubbed LGM-1 short for Little Green Men, sent shockwaves through the scientific community. Here, at last, was the smoking gun, a rhythm so artificial, so deliberate, it had to be the work of an advanced civilization. Or so they thought. The truth was far stranger. Instead of alien engineers, Burnell had stumbled upon the first known pulsar, a rapidly spinning neutron star, the dense corpse of a supernova, beaming radiation from its magnetic poles like a lighthouse cutting through fog. As the star rotated, its beams swept across Earth with clockwork regularity, creating those unmistakable pulses. The discovery earned her advisor a Nobel Prize, though Burnell's own role was controversially overlooked. But the real legacy of LGM-1 wasn't just in rewriting astrophysics textbooks, it was in teaching SETI researchers a brutal lesson about cosmic false alarms. Before pulsars, the search for extraterrestrial intelligence had operated on a simple assumption: unnatural regularity equaled artificiality. LGM-1 shattered that logic. Here was a signal more precise than anything humans could engineer, yet utterly natural. Overnight, SETI protocols had to adapt. The wow signal's one-off blip might have been tantalizing, but pulsars proved even the most convincing patterns could have mundane explanations. The bar for proof was raised indefinitely. Yet LGM-1's story isn't just about dashed hopes. It revealed a universe far weirder than anyone had imagined. Neutron stars, once purely theoretical, were now undeniable objects so dense. A teaspoon of their material would weigh 1 billion tons on Earth, and their pulses. A natural product of physics pushed to the extreme, where gravity and magnetism twist space-time itself. For SETI, the takeaway was clear. The cosmos doesn't need aliens to produce signals that defy intuition. Sometimes reality is bizarre enough on its own. That duality between the allure of contact and the thrill of pure discovery still defines the hunt today. Every time a new signal defies explanation, astronomers face the same delicious tension Burnell did. Is this them, or is it something even more extraordinary? Pulsars taught us to expect the unexpected, and in a universe where dead stars can mimic beacons, maybe that's the most valuable lesson of all. In 2020, astronomers scanning the sky with Australia's ASCAP radio telescope stumbled upon something no one had ever seen before: enormous, faint rings of radio emission, each one spanning hundreds of thousands of light-years. They called them odd radio circles, or ORC cosmic donuts, so massive They could swallow entire galaxies whole. The strangest part, these circles were invisible in optical, infrared, or X-ray light. They existed only as whispers in the radio spectrum, glowing like ghostly halos against the dark canvas of space. At first, researchers assumed they were looking at artifacts, glitches in the data, or distortions caused by telescope calibration. But when follow-up observations with other instruments confirmed the ORCs were real, the mystery deepened. What could possibly create structures this vast, this symmetrical, without leaving any trace in other wavelengths? Theories flew fast and furious. Some suggested shock waves from gargantuan explosions, perhaps the aftermath of two supermassive black holes colliding, rippling space-time like a stone dropped in a pond. Others pointed to galactic winds, streams of charged particles blown outward by furious star formation, though nothing in known physics could explain how such winds would form perfect, isolated rings. Then came the real head-scratcher. ORCs didn't behave like any known astrophysical phenomenon. They weren't tied to active galactic nuclei or starburst galaxies, the usual suspects for energetic radio emissions. Instead, they floated in relatively quiet patches of the universe, as if someone had drawn them there on a whim. Even more puzzling, their structure. Most cosmic explosions produce messy, uneven debris fields, yet ORCs were stunningly symmetrical, their edges crisp as if drawn with a compass. The leading hypothesis now involves something called a reverse shock. Imagine a galaxy expelling enormous bursts of plasma into space at nearly light speed. Over millions of years, that material could slam into the thin gas between galaxies, creating a spherical shockwave that lights up in radio waves as it decelerates. It's a compelling idea, except no one's ever observed a galaxy powerful enough to produce such a clean, colossal bubble. And even if they had, it wouldn't explain why ORCs avoid clustering near known cosmic powerhouses. Perhaps the most tantalizing clue lies in their rarity. Despite scanning thousands of square degrees of sky, astronomers have found only a handful of ORCs. Are they the fleeting aftermath of an ultra-rare cosmic event, like black hole mergers on an unimaginable scale? Or could they be something even stranger, the fingerprints of phenomena we haven't even named yet? Every time a new ORC is discovered, it's as if the universe is teasing us with another piece of a jigsaw puzzle, daring us to guess the bigger picture. Until then, these strange radio circles remain one of astronomy's most beautiful enigmas, silent, colossal, and utterly inexplicable. In August 2015, the Ratan 600 radio telescope in Russia caught something unusual, a sharp, powerful spike pulsing from the direction of HD 164595, a star 94 light-years away, almost indistinguishable from our own sun. Lasting just 2 seconds, the signal blazed at 11 GHz, a frequency with few natural explanations but perfect for interstellar communication. The numbers were staggering. If this was a deliberate broadcast, the energy required would dwarf Earth's total power output, suggesting a civilization capable of harnessing the energy of an entire star. For a brief, electrifying moment, it seemed SETI's decades-long wait might finally be over. Then came the skepticism. The signal never repeated, despite frantic follow-up scans by the Allen Telescope Array and other observatories. Critics pointed out that 11 GHz sits squarely in the band used by military satellites, raising the specter of terrestrial interference. Even the Russian team cautioned against excitement, noting their telescope's wide field of view made pinpointing the exact source like finding a needle in a cosmic haystack. But what made HD 164595's signal linger in scientific memory wasn't just its ambiguity, it was the star itself. This wasn't some distant, hostile red dwarf or unstable young giant. HD 164595 is a near twin of our Sun, slightly older but with a similar temperature and metallicity, traits thought conducive to life. Even more intriguing, astronomers had already discovered a Neptune-like planet orbiting it, hinting at the possibility of unseen, Earth-sized companions in the habitable zone. For SETI, that made the star a prime target, the kind of place an advanced civilization might call home. The signal's timing only deepened the mystery. It arrived during a dedicated survey of Sun-like stars, as if the universe had handed researchers a cosmic hotspot to scrutinize. The aftermath sparked a quiet revolution in SETI strategy. If a star this promising could produce such a tantalizing false alarm, how many others had we overlooked? Traditional searches often prioritized stars with known exoplanets, but HD 164595's signal, real or not, highlighted the flaws in that approach. What if the most likely candidates weren't the ones with planets we could detect, but those whose subtle wobbles or transits hinted at hidden worlds? The debate raged: should we focus on stars with confirmed habitable zone planets, or cast a wider net, trusting that nature might hide its most intriguing secrets in plain sight? To this day, no one knows what caused that 2-second blip. It might have been a glitching satellite, a quirk of atmospheric reflection, or even a cosmic coincidence, a chance alignment of noise mimicking an artificial signal. But HD 164595's legacy endures as a cautionary tale and a beacon. It taught us that the universe's most compelling messages might come from the places we least expect, and that sometimes the hardest part of the search isn't finding a signal, it's knowing when to trust it. For years, astronomers at the Parkes Observatory in Australia were haunted by bizarre signals they called peritons, short, intense bursts of radio waves that looked eerily similar to fast radio bursts from deep space. These signals had all the hallmarks of cosmic mysteries. They arrived from random directions, packed a punch of energy, and vanished without a trace. The only problem, they weren't coming from the cosmos at all. The truth was hilariously mundane. After a painstaking investigation, researchers discovered the peritons had a very earthly origin: office microwaves. Specifically, the signals appeared whenever observatory staff impatiently yanked open the microwave door mid-cycle, releasing a burst of radiation that the telescope, incredibly, could detect. The universe wasn't whispering, it was someone reheating lunch. What makes this story more than just a cosmic punchline is how it exposes a vulnerability in our search for the unknown. Peritons mimicked FRBs so well that for years they muddied the waters of legitimate research. The signals even showed dispersion, a key trait of distant cosmic bursts caused by their journey through interstellar plasma. But in this case, the dispersion was an illusion created by the microwave's radiation bouncing off the observatory's metal structures before hitting the telescope. The fix was simple once the culprit was found: a sign on the microwave reminding staff to wait for the beep. But the lesson lingered. If something as trivial as a kitchen appliance could masquerade as a deep space phenomenon, what else might we be misinterpreting? Peritons became a cautionary tale about human complacency. We expect the universe's secrets to hide in the distant void, not in the break room, yet there's a deeper irony here. The same sensitivity that made Parkes susceptible to microwave interference also made it one of the best FRB hunters in the world. That duality between flaw and feature captures the essence of astronomy. Every breakthrough risks being derailed by the mundane, and every piece of cutting-edge tech has blind spots we don't see until the universe humbles us with a prank. Peritons didn't just teach scientists to double-check their data. They reminded us that sometimes the greatest mysteries are the ones we bring upon ourselves. Tabby's star was already the most mysterious sun in the galaxy before the radio signals came. Astronomers had spent years scratching their heads over its bizarre behavior: unpredictable, dramatic dips in brightness that no ordinary star should exhibit. Some whispered about alien megastructures, vast energy-harvesting constructs orbiting the star, while others pointed to swarms of comets or interstellar dust. Then in 2017, the Green Bank telescope aimed its massive dish at Tabby's star and caught something even stranger: fleeting bursts of radio waves. Suddenly, the cosmic soap opera had a new twist. These weren't just random blips. The signals clustered at frequencies between 1 and 10 gigahertz, a range often eerily quiet in nature, but prime real estate for artificial communication. Even more intriguing, they seemed to vanish when observed with other telescopes, making them frustratingly elusive. Was this a technical glitch or something far more tantalizing? The timing couldn't have been more provocative. Just as the star's odd dimming reached peak controversy, here was a potential smoking gun, radio emissions hinting at technology, not just natural chaos. The alien megastructure theory, once relegated to fringe speculation, suddenly gained fresh traction. Imagine a civilization so advanced it built a Dyson swarm, a colossal array of solar collectors encircling its star to harness energy. Such a structure wouldn't just block light erratically, it might also leak radio noise from immense power transmission or even intentional broadcasts. But before anyone could declare victory for ET, skeptics pounced. The signal's ephemeral nature and lack of repetition screamed interference, possibly from passing satellites or earthly sources. Even the Green Bank team urged caution, noting the emissions didn't perfectly match expectations for an alien beacon. Then came the dust. Detailed studies of Tabby's star's light revealed a telltale signature, uneven dimming across different wavelengths, exactly what you'd expect from fine cosmic dust, not solid megastructures. By 2018, the star's dimming was largely explained by massive, swirling clouds of this dust, likely from shattered comets or colliding asteroids. So where did that leave the radio signals? Most astronomers now believe they were coincidental cosmic static or human-made noise masquerading as something grander. Yet the story isn't just a lesson in dashed hopes. Tabby's star forced science to confront its own assumptions. Before its discovery, no one thought to look for megastructures or alien engineering in telescope data. Now, astronomers routinely scan for technosignatures, subtle hints of technology alongside natural explanations. The radio signals, even if mundane, proved we're asking the right questions. Sometimes the universe's greatest gift isn't an answer, but a mystery that reshapes how we search. 1996 was supposed to be a routine mission for NASA, a space shuttle Columbia deploy a scientific tether into orbit, study electricity generation in space, and bring the data home. But what the crew captured on February 25th would ignite decades of debate. As the 12-mile-long tether snapped and drifted away, cameras recorded something impossible. A cluster of glowing objects swarming near the broken cable, pulsing with eerie synchronization. Then came the audio, a haunting radio signal crackling through the shuttle's speakers like nothing engineers had ever heard. The official explanation pointed to ice particles or debris reflecting sunlight, but the details didn't add up. These particles moved with purpose, darting in formation against the black void. Even stranger, their movements correlated with spikes in the unexplained radio noise, a chorus of static that rose and fell as the object circled the tether. Independent analysts later dissected the footage frame by frame, revealing patterns that defied simple physics. Some objects appeared to change trajectory instantaneously, without the gradual curves expected of orbital mechanics. Others pulsed in time with the signal, as if emitting it. Theories spiraled from the plausible to the extraordinary. Plasma physicists suggested the tether might have become charged, creating glowing discharges that mimicked solid objects. Skeptics dismissed it as lens flares or camera artifacts, but the most chilling hypothesis came from former NASA contractor Donna Hare, who claimed the agency routinely airbrushed UFOs out of satellite images. Could STS-75 have been a rare slip-up, a moment when the veil dropped and something slipped through? What makes the tether incident endure isn't just the footage. It's the signal itself, a raw, unfiltered burst of noise that seems to respond to the objects. When researchers isolated the audio, they found bizarre harmonics buried in the static, repeating at intervals too regular for random interference. One analysis even suggested a fractal pattern, a mathematical signature found in everything from heartbeats to galaxy clusters. Was it a natural resonance from the tether's vibrations or something more deliberate? NASA's final report called it inconclusive, and the tape faded into obscurity. But for those who have studied it, the tether incident remains a Rorschach test for belief. To some, it's proof of otherworldly surveillance; to others, a lesson in how even advanced sensors can deceive us; and for the rest, a reminder that sometimes the most profound mysteries aren't in the distant cosmos but floating right outside our windows. NGC 6946, nicknamed the Fireworks Galaxy for its frequent supernova, delivered one of its most baffling performances in 2017, an X-ray signal that flared with the brilliance of 10 million suns, then vanished without a trace. Unlike the galaxy's usual stellar explosions, this event left no visible debris, no expanding shockwave, nothing but a ghostly afterglow in the data. Astronomers scrambled to explain how something so luminous could disappear so completely, rewriting the rules of cosmic cataclysms in the process. The signal, catalogued as ULEX-4, defied every expectation. Ultraluminous X-ray sources typically come from neutron stars or black holes greedily devouring material, their fierce glow powered by superheated gas spiraling inward. But ULEX-4 burned too bright even for those monsters. Then, within months, its light winked out entirely, a behavior never seen before in such a source. The leading theory, a failed supernova, a star massive enough to collapse into a black hole without the traditional fireworks. Imagine a stellar core imploding so completely, so swiftly, that it skips the explosion phase entirely, swallowing itself whole like a cosmic magician's trick. Yet even that explanation left gaps. Failed supernova should produce a brief neutrino burst, a telltale pulse of subatomic particles, but detectors caught no such signal. Alternative ideas ranged from a star torn apart by an intermediate mass black hole, an elusive class of voids neither small nor supermassive, to a rare tidal disruption event where a black hole shreds a passing star into luminous spaghetti. But ULEX-4's abrupt disappearance didn't fit those scripts either. Most tidal events fade gradually over months or years, not vanish overnight. The real puzzle, though, was location. The Fireworks Galaxy is no stranger to drama, with 9 observed supernovae in the past century alone. But ULEX-4 flared far from any star-forming regions, in a quiet neighborhood where such extreme events shouldn't occur. That isolation pointed to something even stranger. Perhaps a wandering black hole, untethered from any galaxy, had briefly awakened to feast on a rogue gas cloud before slipping back into darkness. What makes this signal unforgettable isn't just its mystery, it's the questions it forces us to ask. How many cosmic phenomena flicker in and out of existence before our telescopes can catch them? Are we seeing anomalies or just the edges of processes we don't yet understand? ULEX-4's greatest lesson might be humility. Even in a galaxy that's earned its pyrotechnic nickname, the universe still has surprises up its sleeve, the kind that don't just explode but evaporate, leaving us staring at the shadows they left behind. The universe is supposed to expand evenly, like rising bread, every galaxy drifting apart in a stately cosmic dance. But in 2008, astronomers stumbled upon something that shattered that tidy picture. Clusters of galaxies weren't just moving outward, they were streaming in the same direction at inexplicable speeds, as if dragged by an invisible hand. They called it dark flow, and its implications were staggering. Either our understanding of gravity was catastrophically wrong, or something beyond the edge of the observable universe was pulling on everything we can see. The numbers were jaw-dropping. Over 1,000 galaxy clusters, each weighing a quadrillion suns, were racing toward the same patch of sky at nearly 2 million miles per hour. That's fast enough to cross the entire United States in less than a second. The kicker, this motion shouldn't exist. after the Big Bang, matter was flung outward in all directions with no preferred side to the cosmos. Yet here was evidence of a cosmic current, a river of galaxies flowing against the tide. Explanations ranged from the radical to the nearly unimaginable. Some theorists proposed a bulk flow, an unseen superstructure of dark matter yanking galaxies like marionette strings. Others dared to whisper about parallel universes. If another bubble universe existed perilously close to ours, its gravity might be leaking through, tugging our galaxies toward it like a magnet under a sheet of paper. The most unsettling idea, dark flow, might be our first glimpse of the true scale of reality, proof that the universe we see is just a speck in an immeasurably larger multiverse, where other cosmic domains exert their pull from realms we'll never reach. Skeptics fought back. Maybe it was a measurement error, a quirk of how we map cosmic microwave background radiation. But when later studies confirmed the anomaly using different methods, even critics had to concede dark flow was real. The question wasn't if it existed, but why. What makes this signal so profoundly humbling isn't just the mystery, it's the scale. Dark flow isn't some local oddity. It's a glitch in the fabric of reality itself, hinting that everything we've ever observed might be a tiny island in an ocean of unseen forces. For centuries, we've mapped the cosmos assuming we could see its edges. Now the universe is whispering back, you haven't even left the shore. The hunt for alien megastructures took an unexpected turn when astronomers noticed stars glowing a bit too warmly in infrared, like cosmic engines leaking heat. Among them, KIC 8462852, better known as Tabby's star, became the poster child for this eerie phenomenon. While its bizarre dimming stole headlines, another clue lurked in the data, an excess of infrared radiation, as if something was absorbing its light and re-emitting it as waste heat. That signature matched a hypothetical blueprint for the ultimate alien power plant, a Dyson Sphere, a vast swarm of energy collecting satellites designed to envelop a star and siphon its energy. But Tabby's star wasn't alone. Dozens of other candidates popped up in surveys, each radiating more infrared than conventional physics could explain. Take Epoch 204548916, a star 230 times more luminous than our Sun, wrapped in a shroud of unexplained warmth. Or TYC 611114021, whose infrared excess spiked so sharply, it looked less like a natural phenomenon and more like construction. The numbers were tantalizing. If even one of these stars hosted a partially completed Dyson swarm, the energy signatures would resemble exactly what telescopes were detecting. Starlight intercepted by megastructures, then irradiated as heat at longer wavelengths. Skeptics pushed back hard. Cosmic dust, they argued, could mimic these infrared excesses beautifully. When a star is young, it's often surrounded by thick disks of debris colliding asteroids, vaporizing comets, or even planetary birth clouds, all capable of absorbing light and glowing warmly in infrared. But there was a catch. Many of these anomalous stars weren't newborns. They were mature, quiet suns where such dust shouldn't exist in such quantities. Worse, some showed no signs of the silicate or carbon grains typical of dust clouds, leaving their infrared glow stubbornly unexplained. The debate reached a fever pitch with two discoveries. First, in 2015, the Gaia spacecraft measured precise distances to several Dyson Sphere candidates and found their infrared excesses weren't from nearby dust clouds but the stars themselves. Then, in 2021, the Lick Observatory's automated planet finder took spectra of another candidate, J2308+0505, revealing its excess heat wasn't just real but asymmetric, as if the swarm around it was lopsided, a hallmark of artificial construction in progress. Yet the most compelling argument against Dyson spheres isn't dust or instrument errors, it's thermodynamics. A civilization advanced enough to build such structures would presumably master energy efficiency, yet many candidates waste staggering amounts of heat, like a car engine spewing half its fuel unused. Wouldn't a Type 2 civilization capable of harnessing stellar power minimize such inefficiencies, unless, of course, the heat is intentional, a byproduct of processes we can't yet fathom, or even a deliberate beacon? The truth, as always, lies in the gaps. For every star that fits the Dyson Sphere profile, there's a plausible natural explanation waiting to be tested. But the sheer variety of these infrared anomalies suggests something profound. Whether they're alien megastructures or undiscovered astrophysical phenomena, they're pushing us to rethink what's possible. After all, the universe doesn't just hide its secrets in darkness. Sometimes they're glowing right in front of us, warm and whispering. Gamma-ray bursts are supposed to follow a simple cosmic script. Short bursts come from colliding neutron stars, long bursts from collapsing massive stars, each one capped by the dazzling finale of a supernova. Then along came GRB 060614, a cosmic rebel that tore up the rulebook. Detected in June 2006, this burst lasted 102 seconds, squarely in long burst territory. But when telescopes swiveled to catch the expected supernova fireworks, nothing happened. The star had vanished without a trace, leaving astronomers staring at empty sky where a stellar explosion should have been. What made this burst so unnerving wasn't just its missing supernova. It came from a galaxy devoid of young, massive stars, the kind that fuel traditional long GRBs. Instead, it lurked in an aging stellar neighborhood where the only plausible culprits were compact objects, neutron stars or black holes. That location pointed to a violent merger, the kind that usually produces short bursts. Yet GRB 060614's marathon duration defied that explanation too. It was as if the universe had mashed together two incompatible cosmic events and dared scientists to make sense of it. Theories flew fast. Some suggested a failed supernova, where a massive star's core collapsed straight into a black hole without the usual fireworks. Others proposed a neutron star merging with a black hole, a rare event that might stretch out the burst's duration as the star spiraled inward, but the most radical idea, that we'd witnessed something entirely new, a quark nova. In this scenario, the neutron star doesn't just collapse, it implodes into even denser quark matter, releasing energy in a prolonged burst that straddles the line between merger and collapse. GRB 060614's ghostly behavior forced astronomers to rethink their categories. Maybe GRBs weren't just short or long, but a spectrum of phenomena with overlapping origins. Subsequent discoveries of hybrid bursts, some with weak supernova, others in unlikely locations, only deepened the mystery. The lesson was clear. When it comes to the universe's most violent explosions, our labels are just placeholders until the next cosmic anomaly comes along to shatter them. Epic 204278916 doesn't just dim, it plummets. Unlike Tabby's star's gradual, irregular dips, this young sun, barely 1/10 the age of our own, drops up to 65% of its light in a matter of days, a freefall so extreme it's like someone flicking a cosmic light switch. Discovered in 2016 by NASA Kepler Space Telescope during its K2 mission, this star's behavior defies every textbook model. Planets can't explain it. Even a Jupiter-sized world would block only 1% of the star's glow. Dust clouds, they'd need to be impossibly thick, swirling in formations no natural process should create. And that's when astronomers started whispering the phrase that electrifies every SETI researcher: alien megastructure. The numbers alone are staggering. Over 78 days of observation, Epic 204278916 exhibited 28 separate dimming events, some lasting mere hours, others stretching weeks. The deepest dips weren't just steep, they were asymmetric, with the star's light dropping sharply before rebooting slowly, like a booting computer. That asymmetry is the smoking gun. Natural dust clouds, even dense ones, dim starlight symmetrically as they pass. but a partial Dyson swarm, a colossal, incomplete ring of energy-harvesting satellites, could cast jagged shadows as its components rotate in and out of view. Skeptics, of course, have counter-arguments. Epic 204278916 is a pre-main sequence star, still cocooned in the gas and dust of its birth nebula. Couldn't clumps in that debris explain the dimming? Maybe, except the star's infrared signature doesn't match typical protoplanetary disks. There's no excess heat radiating from absorbed starlight, no telltale glow of warm dust. Instead, the dimming events coincide with odd fluctuations in the star's magnetic field, as if something massive and artificial were interacting with it. Then there's the star's rotation. Most young stars spin fast, their magnetic fields channeling plasma into predictable patterns. But Epic 204278916's rotation is wrong. It's too slow, as if something or someone has been tapping its angular momentum. Could a Dyson swarm under construction siphon not just light but rotational energy, using it to stabilize or power its framework? It's a wild idea, but the math checks out. A civilization advanced enough to build megastructures might harness a star's spin like a dynamo, converting it into usable force. Yet the most haunting detail isn't in the data, it's in the silence. Unlike Tabby's star, which sits relatively close at 1400 light-years away, Epic 204278916 is a staggering 4,500 light-years distant. If something artificial is there, the light we're seeing left the star when the Great Pyramid of Giza was still new. Whatever's happening there now, construction completed, project abandoned, or never there at all, we won't know for millennia. That's the cruel poetry of cosmic mysteries. Epic 204278916 could be the most compelling evidence of other builders we've ever found, or just another lesson in how creatively nature can fool us. Until we catch another star acting this strangely, all we have are questions. And sometimes the universe prefers it that way. The summer of 1989 brought an eerie twist to the search for extraterrestrial intelligence, a signal that didn't just arrive from space but seemed to answer. Dubbed the boomerang signal, it originated from a transmission sent years earlier by Soviet astronomers, ostensibly as a test of Earth's own radar capabilities. But when a near-identical pulse returned 7 years later, recorded by a Ukrainian radio telescope, the scientific community froze. The timing was impossible. Even if the original signal had bounced off a distant object, the laws of physics dictated it couldn't return so soon, unless something had intercepted and deliberately repeated it back to us. What made the boomerang so unsettling wasn't just its uncanny resemblance to the original transmission, but its bizarre Doppler shift. Natural cosmic echoes, say, from a passing asteroid or ionized gas cloud tend to smear frequencies as they reflect. This signal, though, had a slight but precise frequency drift, as if the mirror sending it back was moving at a steady velocity. The numbers lined up suspiciously well with what you'd expect from an artificial object in orbit around another star, something with enough tech to catch our signal, process it, and fire a reply. Skeptics pounced immediately. The most likely culprit, a secret military satellite, its transmitters accidentally mimicking the Soviet pulse. Cold War secrecy meant astronomers couldn't rule out classified hardware slipping into their data. Others pointed to plasma turbulence in Earth's ionosphere, which can distort and delay radio waves in unexpected ways, but the problem with both explanations was location. The boomerang's echo came from a patch of sky where no known satellites orbited, and ionospheric effects wouldn't preserve the signal's crisp structure so perfectly. Then came the clincher. Independent analysis revealed the signal's polarization was reversed, a hallmark of an intentional phase conjugated reply, a technique used in advanced radar systems to lock onto and retransmit signals with pinpoint accuracy. Was this just a freak natural phenomenon, or something mimicking the very technologies humans had only begun to explore? the debate split researchers down the middle. Some saw it as proof of extraterrestrial tech, a cosmic ping sent back to confirm receipt. Others argued it was a once-in-a-lifetime interplay of cosmic noise and earthly interference, a Rorschach test for wishful thinkers. The truth may never be settled. The original telescope records were lost in the chaos of the Soviet Union's collapse, and no modern scan has ever replicated the event. But the boomerang's legacy lingers as a cautionary tale and a tantalizing what-if. If space ever does echo back, will we recognize the difference between nature's pranks and a hello from the dark? In July 2015, NASA, a Deep Space Climate Observatory, or DSCOVR, sparked a firestorm of speculation when its onboard camera captured something bizarre, a cluster of bright objects streaking across its field of view. Positioned 1 million miles from Earth at Lagrange Point 1, DSCOVR's primary mission was to monitor solar wind and our planet's climate, but that day it seemed to stumble upon something far stranger. The footage showed a string of glowing orbs moving in unison, their trajectory too precise, their formation too orderly to dismiss as cosmic debris. Almost immediately, the internet lit up with theories. Were these alien probes silently surveilling our solar system? Skeptics rushed to offer more mundane explanations. The most plausible: lens flares glare from sunlight bouncing off the camera's optics, warped into orb-like shapes by the instrument's design. DSCOVR EPIC camera, after all, wasn't built for deep space surveillance. Its wide-angle lens and long exposure times made it prone to artifacts, especially when aimed toward the sun. Even the satellite's own team cautioned against overinterpretation, noting similar flares had been documented before. But here's where things got interesting. The objects didn't behave like typical lens flares. They maintained a fixed distance from one another, didn't mirror the sun's position, and most puzzling of all, appeared to dim as they crossed the frame, as if adjusting their luminosity. Then came the counter-arguments from the UFO community. If these were mere optical artifacts, why had similar formations been spotted by other satellites, like the Solar and Heliospheric Observatory, decades earlier? And why did independent analysts tracking the footage note subtle shifts in the object's spacing, almost like a fleet maneuvering in formation? The debate reached a fever pitch when astrophysicist Scott Waring claimed the orbs matched the size and speed of hypothetical von Neumann probes, self-replicating alien drones designed to explore the galaxy. It was a wild idea, but not entirely without precedent. In the 1980s, NASA's own Pioneer and Voyager probes had carried plaques and golden records meant for any civilization that might find them. Could someone or something have returned the favor? NASA's final word on the matter was characteristically measured. While they acknowledged the footage was unusual, they attributed it to a combination of lens effects and cosmic rays, high-energy particles that can create bright streaks in digital sensors. Case closed officially, yet for those who have scrutinized the footage frame by frame, the questions linger. Why did the objects follow such a straight, deliberate path? Why did their brightness fluctuate independently of the camera's exposure settings? And most haunting of all, if this was just a trick of the light, why does space keep showing us the same trick over and over? The DSCOVR mystery isn't just about glowing orbs on a screen. It's a Rorschach test for how we interpret the unknown. To some, it's proof we're not alone. To others, a lesson in the limits of our instruments. But perhaps the most compelling takeaway is this: even our most advanced tools can't always distinguish between a cosmic glitch and a hello from the dark. And until they can, the universe will keep us guessing. Gliese 581G wasn't just another exoplanet, it was a cosmic Rorschach test. When astronomers announced its discovery in 2010, the numbers seemed almost too good to be true. Nestled in its star's habitable zone, this rocky world orbited at just the right distance for liquid water, with gravity strong enough to hold an atmosphere yet gentle enough for life as we know it. But the real twist came when a team analyzing radio data claimed to have found something even more provocative: faint, repeating pulses emanating from the same region of space. Suddenly, the conversation shifted from "could this planet host life" to "did it just say hello?" The signals were achingly ambiguous. Detected by the Rattan 600 telescope in Russia, they appeared as narrowband spikes, the kind that natural cosmic phenomena almost never produce. Even more intriguing, they clustered around a frequency of 1.5 gigahertz, a quiet part of the radio spectrum where interstellar noise fades, making it a logical choice for intentional broadcast. Skeptics immediately cried foul. The signals were weak, barely rising above the telescope's noise floor, and Gliese 581G itself soon became embroiled in controversy. Independent teams struggled to confirm the planet's existence, with some arguing that discovery was just gravitational noise from the star masquerading as an orbiting world. But the debate took a surreal turn when researchers noticed something odd about the signal's timing. Unlike random cosmic static, these pulses appeared to follow a loose pattern, flaring up at intervals that roughly matched the planet's hypothetical orbital period. If Gliese 581G was real, could its rotation be synchronizing with these transmissions? The idea sent chills through the SETI community. On Earth, we time our radar pulses to planetary rotations when studying distant objects. Was something out there doing the same? The scientific backlash was swift. Critics pointed out that Rattan's wide field of view made pinpointing the signal's origin like hearing a whisper in a hurricane. Without precise coordinates, the pulses could have come from anywhere: a passing satellite, a glitching terrestrial transmitter, or even a quasar billions of light years behind Gliese 581. The coup de grace came when improved stellar motion studies suggested the planet might not exist at all, its gravitational signature likely just stellar activity. Yet for all the skepticism, the Gliese 581G saga left an indelible mark. It forced astronomers to confront an uncomfortable truth: the line between noise and evidence isn't just thin, it's porous. What makes this case so haunting isn't the signal itself, but what it represents. In the hunt for extraterrestrial intelligence, hope and interference are locked in a perpetual dance. A flicker of data becomes a Rorschach blot, morphing under scrutiny into whatever we want to see, whether that's a technical glitch or a hello from the stars. Gliese 581G may have faded into obscurity, but its legacy endures as a cautionary tale and a tantalizing what-if. Because sometimes the universe's most profound messages aren't in the signals we catch, but in the questions they force us to ask. The skies above Earth have always been a junkyard of human debris, discarded satellites, spent rocket boosters, fragments of forgotten missions. But in 2018, something lurking in that graveyard started talking. Hawaii's Pan-STARRS telescope first spotted it, a small metallic object designated a 2017 U1, tumbling through near-Earth space with an orbit unlike any known asteroid. At first, astronomers assumed it was just another piece of space junk until the Arecibo radio dish caught it emitting pulses. Not the random crackle of metal twisting in the vacuum, but structured bursts spaced at intervals too rhythmic to ignore. What made this object so unnerving wasn't just its artificial-seeming signals. It was the material. Spectroscopic analysis revealed a surface unlike natural space rock, a strange, radar-reflective metal alloy eerily similar to spacecraft shielding. Yet no nation claimed it, and its trajectory didn't match any recent launches. The more researchers studied it, the more the explanations split. Mainstream astronomers pointed to a spent booster from some secret Cold War mission, its decaying insulation exposing conductive layers that resonated with solar radiation. But a vocal minority noted something odd. The pulses weren't static. They shifted subtly over time, as if the object were adjusting its emissions. The conspiracy theories wrote themselves. Could this be a relic of extraterrestrial tech, a probe parked in Earth's backyard to monitor or even communicate? the idea wasn't entirely fringe. In the 1960s, astronomers like Ronald Bracewell had theorized about self-replicating probes, alien machines designed to loiter in star systems, gathering data and signaling home. A 2017 U1's metallic composition and erratic orbit fit that speculative blueprint disturbingly well. Even its size, roughly the shape of a cigar, matched descriptions of the infamous Oumuamua interstellar visitor spotted a year earlier. Coincidence or a pattern, skeptics countered with Occam's razor. Space is littered with defunct human hardware, some dating back to the dawn of the space age. Objects like the Vanguard 1 satellite, launched in 1958, still orbit silently, their aluminum skins pitted by micrometeorites. Couldn't this just be another forgotten artifact, its radio emissions caused by some mundane interaction with Earth's magnetosphere? The problem with that theory was timing. The pulses peaked when the object was farthest from Earth, a point where terrestrial interference should have been weakest. If it was space junk, why wasn't it behaving like any other piece of scrap? The truth, as often happens, may lie in the gaps. A 2017 U1 could be a fragment from an off-the-books military satellite, its classified components behaving unpredictably as they degrade. Or it might represent something entirely new, a natural phenomenon we've never catalogued, like metallic asteroids that act as cosmic radio transmitters when bathed in solar wind. But the most tantalizing possibility remains the hardest to prove, that we're not alone in the debris field, and something out there has been listening far longer than we've been broadcasting. One thing's certain: the next time an odd metal object winks at us from the dark, we'll be watching closer than ever. In October 2017, astronomers spotted an object streaking through our solar system unlike anything they'd ever seen. A slender, tumbling rock they named Oumuamua, Hawaiian for scout. At first, it seemed like just another interstellar visitor, the first confirmed from beyond our star system. But then, Oumuamua started breaking the rules. As it slingshotted past the sun, telescopes caught something bizarre. The object was accelerating as if pushed by an invisible force. Not the gentle nudge of solar radiation, but a sudden, unexplained burst of speed that defied every law governing celestial mechanics. Mainstream science scrambled for explanations. Could outgassing the release of trapped gases as Oumuamua warmed account for the kick? Problem was, no telescope detected the telltale plume of dust or vapor that should have accompanied such an event. Others suggested Oumuamua might be a cosmic iceberg, made of hydrogen so pure it would vaporize invisibly in sunlight, but even that theory stretched credibility. Hydrogen ice is fragile, unlikely to survive the journey between stars. Then came the fringe theories, the ones that made headlines. Harvard astrophysicist Avi Loeb proposed a radical idea. What if Oumuamua wasn't a rock at all, but a relic of alien technology? Its peculiar shape, possibly elongated like a pancake or cigar, and its sudden acceleration aligned uncomfortably well with concepts for light sails, spacecraft propelled by starlight. Loeb argued that Oumuamua's trajectory, too precise to be random, suggested directed motion. The backlash was swift. Critics accused him of sensationalism, pointing out that extraordinary claims require extraordinary evidence, and Oumuamua, already fading into the void, left little to analyze. The truth might lie somewhere in the shadows. Oumuamua's acceleration could stem from a phenomenon we've yet to discover, a new class of cosmic object that behaves unlike anything in our playbook. Or perhaps it was a fragment of a larger body, shattered long ago, its unique composition giving rise to odd dynamics. But here's the unsettling takeaway. If Oumuamua was artificial, it's already gone. Hurtling past Neptune by now, it carries its secrets into the dark, leaving us with nothing but questions. What makes Oumuamua so haunting isn't the mystery of its origin. It's the realization that the universe might be teeming with objects like this, slipping through our solar system unseen. We barely noticed this one. How many others have we missed? And the next time something strange drifts into view, will we be ready? Or will it, too, vanish before we can decide if it's a rock, a relic, or something in between? High above Earth, silent and mysterious, a shadow has lurked in orbit for decades, at least according to legend. The so-called Black Knight satellite is one of space's most enduring myths, a tale of an ancient alien probe watching over humanity since before the space age began. The story goes like this. In 1954, newspapers reported that the U.S. Air Force had detected a mysterious object in polar orbit, an impossible feat for any nation at the time. Then, in 1960, ham radio operators claimed to intercept strange signals they traced to the same phantom satellite. Conspiracy theorists insisted this was no human-made device, but a relic of extraterrestrial intelligence silently observing us for millennia. The truth, however, is far stranger and rooted in the very human chaos of the Cold War. The first cracks in the Black Knight legend appeared when researchers traced its supposed origins. That 1954 newspaper article, it was referencing a scientific prediction about future satellites, not an actual discovery. As for the radio signals, they matched known natural phenomena, cosmic noise bouncing off the ionosphere, misinterpreted by overeager listeners. But the myth's real unraveling came from NASA itself. In 1998, spacewalking astronauts photographed a peculiar object drifting near the space shuttle. Conspiracy forums erupted, declaring it proof of the Black Knight, until experts identified it as a thermal blanket lost during an earlier mission. The image, stripped of context, became fuel for the fire, even though the explanation was mundane. What makes the Black Knight myth so stubborn isn't just the allure of ancient astronauts, it's how it reflects our own technological anxieties. During the Cold War, both the U.S. and USSR launched secret satellites, some of which were only declassified decades later. When strange objects did appear on radar, they were often fragments of failed missions or classified payloads. In that climate of paranoia, it was easy for imagination to fill the gaps. Even Nikola Tesla got dragged into the legend, with claims he'd intercepted alien transmissions in the early 20th century. In reality, Tesla was likely picking up distant pulsars, natural cosmic radio sources, but the idea of a lone genius cracking an interstellar code was too tantalizing to dismiss. The Black Knight's staying power reveals something profound about how we process the unknown. When faced with the vastness of space, we're quick to impose narratives, whether they're tales of ancient watchers or secret government projects. And while no evidence supports the idea of an alien satellite, the myth endures because it taps into a deeper question. If something were out there, how would we even know? In the end, the Black Knight isn't just a story about space. It's a mirror reflecting our own hopes, fears, and the eternal itch to find meaning in the static. Long before telescopes could peer into the depths of the solar system, astronomers in the 19th century were convinced they'd found something impossible, a hidden world tucked between Mercury and the Sun. They called it Vulcan, a phantom planet whose existence wasn't just theorized but seemingly observed. The evidence, peculiar wobbles in Mercury's orbit and fleeting dark spots glimpsed during solar transits, signals that vanished as quickly as they appeared. The hunt for Vulcan became one of science's most stubborn blind alleys, a cautionary tale about how easily we can mistake noise for discovery. The irony is that the Vulcan myth wasn't born from wild speculation but rigorous calculation. When mathematician Urbain Le Verrier noticed Mercury's path didn't quite obey Newton's laws, he assumed an unseen planet's gravity was tugging it off course. It was the same reasoning that had led him to predict Neptune's existence years earlier, a triumph that cemented his reputation. So when amateur astronomer Edmond Modest Lescarbault claimed to spot a tiny dot crossing the Sun in 1859, Le Verrier seized it as proof. The scientific world celebrated until other observers failed to replicate Lescarbault's sighting, and Vulcan slipped back into the shadows. What makes this centuries-old ghost story relevant today are the eerie parallels to modern signal hunting. Those 19th century astronomers weren't careless. They were victims of the same pitfalls that still trip us up: instrumental artifacts and confirmation bias. The dark spots they saw were likely sunspots or flaws in their telescope lenses, misinterpreted through the lens of expectation. Even the orbital anomalies had a mundane explanation, one that wouldn't come until Einstein's theory of general relativity revealed Mercury's wobbles weren't caused by a hidden planet but the warping of spacetime itself. The Vulcan saga's real legacy isn't in its errors but in how stubbornly the idea persisted. For decades, credible astronomers reported Vulcan sightings, their observations muddied by atmospheric distortions or equipment glitches. Sound familiar? It's the same pattern we see with modern mystery signals, fleeting radio blips or optical anomalies that vanish under scrutiny. The difference is we now have tools to question our assumptions, yet the allure of the unknown still tempts us to fill gaps with fantasies. Perhaps the most poignant lesson comes from what didn't happen. When Einstein's equations finally explained Mercury's orbit without Vulcan, science didn't mourn the lost planet, it marveled at a deeper truth. That's the heart of discovery. Sometimes the universe's greatest gifts aren't the answers we expect, but the questions we didn't think to ask. And if a phantom world could lead us to relativity, what might today's unexplained signals be steering us toward? Rising like ghostly towers above and below the Milky Way's bustling disk, the Fermi bubbles stretch 50,000 light-years into the void, cosmic smokestacks belching radiation we still don't fully understand. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these colossal structures glow with high-energy gamma rays and radio waves, their edges crisp as if someone had blow-torched the galaxy's poles. But the real enigma lies at their roots. Sagittarius A, our galaxy's supermassive black hole, dormant now but possibly the architect of this staggering celestial graffiti. For scale, imagine the entire visible night sky and then some. The bubbles dwarf everything we know, their towering plumes extending far beyond the Milky Way's spiral arms. Initially, astronomers assumed they were remnants of star formation, the cumulative exhaust of billions of supernovae, but the energy signature didn't fit. The gamma rays here were too intense, too focused, as if carved by a single cataclysmic event. That's when attention turned to the sleeping giant at our galaxy's heart. Sagittarius A might seem quiet today, but the Fermi bubbles suggest a violent past. One leading theory posits that 6 million years ago, the black hole gorged itself on an enormous gas cloud, its subsequent indigestion erupting in twin jets of relativistic particles. These jets, blazing outward at nearly light speed, would have punched through the galactic halo, inflating the bubbles like cosmic bellows. Supporting this is the presence of microwave haze, a fog of high-energy electrons shrouding the bubbles, exactly what you'd expect from ancient jet material slowing down and diffusing over millennia. Yet not all the pieces fit. The bubble's symmetrical structure is too perfect, their edges too sharply defined for something supposedly billions of years old. Some researchers argue for a more recent origin, perhaps a series of smaller black hole meals, each topping up the bubble's energy like a celestial battery. Others propose an even wilder idea: dark matter annihilation. If hypothetical WIMP, weakly interacting massive particles, collide near the galactic center, they could theoretically produce the gamma rays Fermi observed. It's a long shot, but the bubble's sheer scale forces scientists to consider every possibility, even the exotic. Then there's the radio whisper. While gamma rays dominate the bubble's profile, their faint radio hum tells another story. In 2020, the Meerkat Array in South Africa mapped this emission in unprecedented detail, revealing delicate filament structures woven through the bubbles like cosmic lace. These threads resemble those seen near active black holes in other galaxies, bolstering the jet theory. But here's the twist: some filaments curve against the bubble's expansion, as if tangled by invisible magnetic fields. Whatever sculpted these features didn't just blast energy outward, it orchestrated it. What makes the Fermi bubbles so mesmerizing isn't just their origin story. They're a living laboratory, a chance to study how galaxies vent their energy into the cosmos. Similar structures have been spotted in Andromeda and distant quasars, suggesting this might be a universal black hole rite of passage. For us, it's a front-row seat to the Milky Way's tempestuous adolescence, proof that even quiet galaxies have explosive pasts. And somewhere in that faint radio crackle, there might still be echoes of the meal that started it all, a black hole's belch reverberating across millennia. Dark matter is the universe's most frustrating paradox, a substance that makes up 85% of all matter, yet refuses to reveal itself except through gravity's ghostly tug. But what if we've been searching in the wrong spectrum? In 2014, a team of astronomers dropped a bombshell hypothesis: dark matter might be whispering to us in radio waves. The idea hinges on an obscure phenomenon called dark lightning, where hypothetical dark matter particles could interact just enough to emit faint, diffuse radio static as they collide. This wouldn't be the sharp, deliberate signal of an alien broadcast, but a cosmic murmur woven into the background noise of the universe, a hum we've overlooked because we weren't listening for it. The theory gained traction when researchers noticed odd radio emissions from distant galaxy clusters, regions where dark matter should be densely concentrated. These signals, detected by the Very Large Array in New Mexico, didn't match any known astrophysical process. No star formation, no black hole activity, just a persistent, unexplained glow. The kicker: the frequency of these radio waves lined up eerily well with predictions for actions, one of the leading dark matter particle candidates. Actions are theorized to convert into photons light when they pass through strong magnetic fields, meaning galaxy clusters, with their turbulent magnetic environments, could essentially turn dark matter into detectable radio static. Of course, skeptics pounced. The radio emissions could just as easily come from undiscovered astrophysical processes like turbulent plasma or exotic particle acceleration. Even the action explanation has hurdles. These particles are supposed to be ludicrously light, a billionth the mass of an electron, making their radio signature absurdly faint. But here's where things get clever. Scientists realized that if actions are responsible, their radio signature would shift slightly depending on the density of dark matter in a given region. That's a fingerprint we can test. Projects like the Dark Matter Radio Experiment are now fine-tuning ultra-sensitive detectors to scan for these subtle variations, turning entire galaxies into dark matter microscopes. Meanwhile, another team is taking a radically different approach. Instead of waiting for dark matter to speak, they're trying to force a conversation. The Casper experiment uses powerful magnetic fields to nudge hypothetical dark matter particles, hoping to provoke just enough interaction to produce a detectable radio pulse. It's like tapping on the walls of reality, listening for an echo from the other side. The stakes couldn't be higher. If these experiments succeed, they won't just solve one of cosmology's biggest mysteries, they'll open an entirely new window onto the universe, one where dark matter isn't just an invisible scaffold, but a dynamic, humming layer of reality we've only just begun to hear. The irony is delicious. After decades of chasing dark matter through billion-dollar particle colliders and underground labs, the breakthrough might come from the oldest tool in astronomy, a radio antenna. And if that faint static ever resolves into a pattern, it'll rewrite our place in the cosmos. We've spent centuries assuming darkness meant silence. What if it's been singing all along? From the haunting echo of the wow signal to the enigmatic pulses of fast radio bursts, these 25 cosmic anomalies remind us just how vast and baffling the universe truly is. Some signals, like the Oumuamua burst or the Fermi bubbles, have reshaped entire fields of science. proving that even the strangest blips can rewrite textbooks. Others, like the Black Knight satellite or the boomerang signal, serve as cautionary tales, reminders of how easily human imagination can blur the line between interference and revelation. Yet whether debunked or still unexplained, each signal shares one vital trait. It pushed us to look deeper, question harder, and refine the tools we use to listen to the cosmos. Take the repeating FRBs. A decade ago, they were dismissed as glitches or one-off cosmic accidents. Now we know they're a window into extreme physics, possibly tied to magnetars or even, dare we say, alien engineering. And then there's dark flow, a mystery so profound it hints at forces beyond the edge of our observable universe. These aren't just curiosities, they're catalysts. Every unexplained signal forces science to adapt, whether by building better telescopes, devising new theories, or humbly admitting, we don't know yet. That's the beauty of the hunt. The answers matter, but so do the questions they inspire. So what's next? The universe isn't done surprising us. New telescopes like the Square Kilometre Array will scan the sky with unprecedented precision, while AI sifts through data for patterns no human could spot. Maybe the next big signal is already hiding in plain sight, waiting for the right mind to crack its code. Or maybe it's lurking in the static just beyond our reach for now. One thing's certain, the cosmos is a master storyteller, and we're only on the first page. Whether you're here for the science, the mystery, or the thrill of the unknown, stay curious. The next signal could be the one that changes everything, and if you want to be there when it happens, hit subscribe because the universe never stops talking. We just need to keep listening.